Hello and welcome. This is the Taming Wild AI channel where we bring AI technologies out of the wild using the best practices of software engineering. A few weeks ago, we started taming the author's implementation of efficient neural architecture search. The implementation has 4 execution scripts. CFAR10 macrosearch.sh performs macro search over convolutional networks of a specified depth. It searches through layer types and connectivity configurations for a network that performs well on the CFAR10 classification task. CFAR10 macrofinal.sh trains from scratch a network that was found from macro search. The script successfully trained a 24-layer network to 93% accuracy. But when we took an actual output from the previous script and gave it to this one, we ran into some errors suggesting incomplete code. CFAR10 microsearch.sh performs microsearch over small, convolutional, and reduction cells. It also searches through layer types and connectivity configurations, but the cells it generates are repeated and then connected together to form a network that performs well on the CFAR10 classification task. CFAR10 microfinal.sh trains from scratch a network whose convolution and reduction cells were found from microsearch. The script successfully trained a network defined by the previous script to 93% accuracy. Now, one of the items on my to-do list for taming efficient neural architecture search was conversion to mainstream TensorFlow 2. The scripts are currently running in TensorFlow 2, but they depend on numerous functions in the compat.v1 namespace. Many of these are generating deprecation warnings. This means the scripts are very brittle. They're going to stop working in the near future when an upgraded version of TensorFlow is released. In the last episode, we looked at the steps we can take to convert a simple TensorFlow 1 script to TensorFlow 2. The first step was string substitutions to replace TensorFlow 1 calls with TensorFlow 2 calls from the compat.v1 namespace. We already did this for efficient neural architecture search, otherwise it wouldn't run at all in TensorFlow 2. Another step was replacing session.run with direct function calls. In the last episode, this required us to wrap a couple of TensorFlow 2 calls in Python functions. In a couple of other cases, the TensorFlow 2 calls returned a Python function that we could call. In previous episodes, we got unit tests working that covered 97% of the code. This makes me tempted to start replacing these calls to session.run with direct function calls. But our unit tests don't cover code paths that actually go through session.run into other parts of the code. Instead, they are using mocks of the session.run method. So let's do the proper thing. We'll add session.py to our tests directory under integration/cfar10. And write tests that cover some of these paths.
Let the code flow.
Okay, I wrote a test for running a training step for the child model in macro search. This code is copied directly from the train function. I had to create a session context manager. I used the config parameter because that allows placement of graph operations on CPU or GPU, whatever the operation is compatible with. I had to get the operators, and I did it the same way as in the train function. I had to set the command line flags, so I used the restore flags context manager to restore them when the test is complete. The settings themselves are all from cfar10 macro search.sh. I had to get the training data, and I did it the same way as in the train function. Now this test will only work on a GPU instance, so there's no point in trying it on my Mac Mini. Alright, I've written 4 integration tests for microsearch, microfinal, macrosearch, and macrofinal. I added assertions to make sure values are being returned from the operators and that they are sane. I also added with tf.graph.asDefault to create a separate graph for each test. Otherwise, the tests were interfering with each other. The tests are passing now on a GPU instance, although I'm getting a lot of deprecation warnings and even an error at the end about an unused object. Next, I would like to replace these calls to ses.run with direct function calls to ensure I'm getting the same values. However, a lot of changes are required to get this to work. Under TensorFlow 1, these values are set to tensors, nodes in the computation graph. This repository uses all of these TensorFlow calls to build a very large computation graph for the child and controller models. The computations don't get executed until ses.run is called, in this case for the child model. Under TensorFlow 2, we have to make sure that these values are callable. As we saw in the previous episode, some TensorFlow 2 calls return callable functions, but others eagerly perform computations. In the latter case, we'll have to wrap them in functions to prevent them from being executed before everything is ready. This repository makes heavy use of the TensorFlow 1 variable scope context manager. This creates a namespace for variables in the execution graph. There's a TensorFlow 2 function that does the same thing, name scope. However, variable scope can also specify whether new variables should be created in its context or existing variables should be reused. And remember, reuse of previously trained weights is a key innovation of efficient neural architecture search. Variable scope can also specify the initialization method for variables created in its context. For these reasons, I had to introduce a weight manager class. All variables are now created or gotten through the weight manager get method, and the reuse and initialization parameters, which were passed to variable scope, are passed to it. Under delayed execution, I ended up with code that composed TensorFlow API calls, like this. This code would create a graph that was not directly visible, and the graph would not get executed until I called session.run. The mainstream TensorFlow 2 equivalents would sometimes execute operations immediately, but sometimes they would return a function that would have to be called later. If I started replacing these calls, I would have to rewrite a large amount of code before I could test a working code path in TensorFlow 2. I needed an incremental way to make the execution graph a little easier to see and also control whether the API call happened immediately or was delayed. I took inspiration from other frameworks and from other parts of this code base. Here's what I did. I put the composed API calls in a list. Because they were composed on each other, we can execute them using this for loop that just passes the return value of the last one on to the next one. Some of the API calls take other arguments besides the return of the composed calls. By wrapping those calls in a lambda, we create a kind of partial function that takes a single argument. My solution was to delay the execution of the TensorFlow API calls until this object was called. All the TensorFlow API calls currently are delayed execution, so I call the object immediately. But this sets us up to replace the API calls with immediate TensorFlow 2 API calls and call the object later. Classes like this also represent parts of the execution graph in a simple, reusable way. This call function, which composes layer upon layer, kind of performs the same function as session.run. Note that I have not altered the execution of the code in the slightest. My unit and integration tests continue to pass. But by sending the execution through a class in this way, I've set myself up for an easier transition to mainstream TensorFlow 2 API calls. I spent several days adding classes that make the execution graph easier to see and controlling whether an API call happened immediately or was delayed. I started the transition to mainstream TensorFlow 2 API calls by adding integration tests. There's one test each for macro search, macro final, micro search, and micro final. Instead of testing on the full CFAR10 dataset, I've created small NumPy arrays. The flags for each test match the flags specified in the shell scripts, except of course I'm using a batch size of 1 because of my small data set. I've modified Connect Controller to be a bit more functional. It was using side effects, setting member variables to various operators in the execution graph. Those parts of the graph were executed in the context of session.run. Now it returns callable functions that perform those operations in TensorFlow 2. For each batch of training images and labels, we calculate the model's prediction on the images, then calculate the loss with respect to the labels, and then use the loss to adjust weights. This training loop looks more like what we've seen in previous videos for other models. No feed dicts or session.run like in TensorFlow 1. In fact, the changes I'm having to make are surprisingly similar to the changes I made in the previous video. Replace a TensorFlow 1 call with a TensorFlow 2 call, but wrap it in a function or lambda to ensure it is only executed when its arguments are actually available, and pass those arguments into the function or lambda instead of relying on the graph to retrieve them. While making these changes, I discovered a nasty bug in the original code. This code gets a batch of images X. The batch is a multidimensional array in one of two formats. NHWC means the first dimension ranges over the number of images in the batch. The second dimension ranges over the pixel rows of an image. The third dimension ranges over the columns of a pixel row. And the fourth dimension ranges over the channels of a pixel. The original data has 3 channels for red, green, and blue, but convolution operations may increase the number of channels. NCHW is an alternative ordering of those same dimensions. Global average pool performs an averaging operation over the entire image. This code performs a different reduce mean operation depending on the format. But regardless of the format, the result is in NC format, a dimension for the image number in the batch and a dimension for the channel. Here, the code is creating weights for every channel. However, the earlier code incorrectly assumes that the input is still either NHWC or NCHW. For NHWC, it intends to get the fourth shape element as the number of channels. For NCHW, it takes the second shape element as the number of channels. Not only is there a typographical error, which disallows NHWC, but considering the result is in NC format, we can take the second shape element as the number of channels in either case. Our unit tests exposed the typographical error, and the integration tests exposed the error in the logic of the code. I've been struggling with a very interesting problem for several days. This is the original TensorFlow 1 code that defines the training step for the child model in macro search and macro final execution. Similar code defines the training step for the child model in micro search and micro final. The call to model defines the child model's execution graph along with all of its trainable weights. When run in the context of a session, this execution graph will calculate the forward pass for the child model. Self.loss is the execution graph for the loss function. You can see that it's defined in terms of the model's output and the trainable labels. GetTrainOps defines the backward pass for the model. Self.trainOp is the execution graph that calculates the gradients of the loss with respect to the trainable weights and then adjusts those weights. Of course, none of that actually happens until self.trainOp is run in the context of a session. But the trainable weights are collected here and used in the definition of self.trainOp. Unfortunately, in TensorFlow 2, there is no simple call to collect trainable variables. Indeed, the documentation clearly states that you should create a container for your trainable variables. In the last video, we used this recommended method. The trainable variables were stored in the model layers, and we got a list of the trainable variables through the trainable variables attribute. Note that for the controller models, the code has always had a separate method, createParams, that creates the necessary trainable variables and stores them as members of the controller object. The problem is that for the child models, the TensorFlow 1 code creates or retrieves trainable variables on the fly during definition of the graph. The shapes of these variables are dependent on the shapes of various tensors generated during the forward pass. This might seem necessary because the child model is modified during the course of the search, but the child model is certainly not modified during the course of its own execution. So it should be possible to create trainable variables when the candidate child is sampled from the controller, and then use those variables during the forward and backward passes. I spent a lot of time trying to separate the creation of the child model variables from the execution of the child model, similar to what is done for the controller model. Otherwise, in TensorFlow 2, I would have to do something strange. I would have to execute the child model once just to acquire a collection of the trainable variables. I did this by going through the little layered models classes that I introduced earlier and making sure that in all cases the weights are defined in the initializer and not during the call of the object, which is the forward pass through this small model. I've spent several more days making changes to the code, separating the creation of child model variables from execution of the child model. In fact, I made so many changes that I felt the need to test them by running all 4 scripts to completion on a GPU. My unit and integration tests ensured for the most part that everything was still working correctly. The remaining problems were easy to track down and fix. Sure enough, my session.py tests are looking similar to what I was going for. It looks like the code calculates the model's predictions on the images, then calculates the loss, then uses the loss to adjust the weights. Instead of storing tensors, This dictionary now stores instances of the layered model classes. The weights of the model were created when the classes were instantiated. Here, the instances are being called, which results in execution of the TensorFlow compat.v1 functions. Those functions operate on the input and on the weights and return tensors. The tensors are then passed to ses.run, which executes the graph operations. Next, I'll replace the compat.v1 calls with mainstream TensorFlow 2 calls. Those calls will execute the graph operations immediately or eagerly, and I'll be able to eliminate the ses.run call here. All right, I have good news and bad news. The good news is that the conversion to TensorFlow 2 is complete. All of the compat.v1 namespace calls have been replaced with mainstream TensorFlow 2 calls. The deprecation warnings are also gone. I worked hard to separate the construction of weight variables from execution of graph functions. This paid off because several TensorFlow 2 calls return callable objects instead of graph tensors. I was simply able to move such calls out of the call method and into the initializers of the classes I introduced. Here's a few changes that were more complicated. I removed calls to tf.compat.v1.flags. Instead, I added absol.py to the requirements.txt file and used flags according to its documentation. I've removed the calls to disable eager execution Like in the last video, I've removed the calls to graph and removed the calls to session. I've added some TensorFlow functions to accelerate training operations for the controller and child models. A lot of the deprecation warnings were telling me to use data pipelines, so I've done that as well. Now for the bad news. Most importantly, the macro search and macro final scripts have stopped training to convergence. Micro search and microfinal seem to be working fine, but I inadvertently introduced a breaking change. It was probably either in the macrocontroller.py or the macrochild.py. The deprecation warnings are gone, but now I'm getting some other warnings. The original code was using a sync replicas optimizer. This appears to allow for distributed training across multiple devices. In efficient neural architecture search, it was being used for gradient accumulation. I couldn't find a simple replacement for that function in TensorFlow 2. Fortunately, dropping gradient accumulation didn't seem to affect micro search or micro final, so I don't think this was a breaking change. I also dropped the saving of the model during training. This allows training to resume if it gets interrupted, but it was never clear how to do so in the first place. Subscribers have probably noticed that this video has been 3 months in the making. It would have taken less time if I was working on this full time or with some help, but there was a ton of work to do. By the way, if you'd like to help out with this channel, please drop me a note at the email address in the notes. I'm honestly tired of working on this model, especially when there are more topical technologies to cover. Unless there's an outcry in the comments, I'm going to put neural architecture search on the back burner. Thank you for your patience. Thank you for tuning into this episode, and please stay tuned. I'm hoping to publish shorter videos more frequently in the future. If you found this video to be instructive or useful, please share it with other people. Don't forget to click the like and subscribe buttons, and I also welcome all of your constructive comments.